Welcome to this session on extended reach drilling, Module 3 of 3. In this submodule, we will examine the technical and operational aspects of ERD, from mud properties and drilling parameters to casing, cementing, and completions. We'll also review project challenges and the systems approach that makes ERD feasible. In this module, we'll focus on the practical aspects of extended reach drilling. We begin by reviewing mud properties, where we'll see how rheology, fluid loss, and lubricity have a greater impact on hole cleaning and ECD management in long horizontals. Next, we move into drilling efficiency strategies and parameters, highlighting how flow rate, rotation, and disciplined cleanup practices shape performance. From there, we'll examine hole condition monitoring, where the most reliable indicators come from pickup and slack-off trends rather than torque or ECD alone. We'll then turn to casing design and running procedures, where drag and buckling are the defining challenges, followed by cementing, with its added complexity in horizontal displacement and centralization. The module continues with completions, where interventions and deployment planning are critical, and project operations, where rig limits, logistics, and costs must be carefully managed. Finally, we'll review the systems approach, tying together these elements, and conclude with a summary of the key technical issues that define ERD performance. When it comes to mud properties in extended reach drilling, it's important to note that what works in a vertical well does not necessarily work in a horizontal section. Rheology that looks perfectly acceptable in vertical drilling may lead to inadequate hole cleaning in long horizontals. This is why we follow guidelines for low-end rheology, to ensure that annular cuttings remain suspended, particularly at low flow velocities. ECD, or equivalent circulating density, is also much more sensitive to mud properties in ERD wells. Small changes in viscosity or density can create large shifts in ECD, which in turn affects wellbore stability and fracture pressure margins. Fluid loss control and inhibition are critical, as cuttings dispersion can reduce transport efficiency and damage formation integrity. Lubricity also plays a bigger role in ERD, because we often rely on conventional drilling methods across extended intervals. Finally, we must consider long-term effects on tools, such as erosion from extended exposure and reduced signal strength in MWD/LWD systems. Now that we've set the foundation with fluids, let's move into drilling efficiency strategies and parameters. Efficiency in ERD is less about speed and more about endurance, similar to an endurance race. The fastest route isn't always the most successful. Instead, we need strategies that balance progress with maintaining wellbore stability and equipment performance. Think of pit stop strategies. Sometimes pausing for hole cleaning is faster overall than pushing too hard and risking instability. Drilling parameters in ERD must be approached differently. Flow rate and pipe rotation are both critical, but their relative importance shifts compared to vertical wells. Maintaining circulation helps clean the hole, while rotation assists with cuttings transport along the low side. We also use special techniques for connections and breaking circulation, as these points are particularly vulnerable to stuck pipe or cuttings settling. Likewise, RPM and the duration of hole cleanups before trips are critical. Skipping this step often leads to back reaming or extended downtime later. So, in ERD, success comes from disciplined parameter management rather than sheer ROP. From here, let's examine how we monitor hole conditions to ensure stability. In extended reach wells, the data we rely on to judge hole condition is very different from conventional drilling. Torque and ECD, while useful, are actually poor indicators of hole cleaning efficiency in long horizontals. Instead, the most critical values to watch are slack-off and pick-up loads, which tell us how much drag is building up in the string. The interpretation of these trends is far more important than the raw values. For example, gradual increases in pickup weight can indicate cuttings accumulation, while sudden shifts may point to mechanical sticking or key seating. Unlike vertical wells, single point data has limited value. It's the trend over time that reveals the true condition of the wellbore. Because ERD wells are more prone to instability and cuttings transport issues, proactive monitoring is essential. Spotting problems early allows us to respond with circulation or conditioning before serious complications develop. With that monitoring mindset established, let's now look at casing design and running procedures, one of the areas where drag and buckling become defining challenges. In extended reach wells, casing design and running procedures often become the critical bottleneck. The main challenge is overcoming drag and buckling. With long departure lengths and shallow true vertical depth, the casing experiences much higher axial and lateral forces compared to conventional wells. One key point is that where casing stops in the hole is actually quite predictable, provided the right modelling and tools are used. If we don't plan properly, casing may stall before reaching target depth. However, with careful modelling and by applying friction reduction techniques, we can extend the reach considerably. Relatively simple methods such as centralizer spacing and circulation practices can greatly improve casing run length. Beyond that, casing flotation systems, where part of the casing is filled with lighter fluid or air until reaching depth, can significantly reduce drag. Getting casing to bottom is one of the biggest hurdles in ERD. Without success here, completions cannot proceed. That brings us naturally to the next stage, cementing, which has its own set of challenges in extended reach drilling. Cementing in extended reach wells is a very different challenge compared to vertical operations. The displacement process, both inside the casing and in the annulus, becomes much more difficult over long horizontal intervals. Fluids tend to channel, either along the high side or low side of the hole, leading to poor zonal isolation. Centralization is critical, but harder to achieve in high angle and horizontal sections. Without proper centralizers, mud channels remain, and cement cannot fully displace the drilling fluid. Pipe movement, both reciprocation and rotation, is one of the best tools we have to improve displacement, but in ERD, this requires careful planning because torque loads are high. Liner rotation in particular can be limited by friction and buckling, so torque and drag analysis must be done ahead of time. The key takeaway is that cementing design for ERD requires a higher level of planning and execution discipline than in conventional wells. Once the well is cemented, the next critical stage is completions, where drag and buckling issues often reach their peak. Completions in ERD wells present some of the toughest operational challenges. Drag and buckling, which were already significant for drilling and casing, become even more critical when deploying completion assemblies. Long, heavy strings, such as sand control screens, packers, and liners, must be run into the well with very little margin for error. Often, completion operations require detailed intervention planning well before the drilling phase is finished. This means thinking ahead about wireline, coiled tubing, or tractor conveyance options in case tools cannot reach bottom under their own weight. Intervention in extended reach wells is always more complex, more time-consuming, and more expensive, so planning every scenario is essential. Overall, completions in ERD wells require not only engineering analysis, but also operational creativity, balancing mechanical limits with the need to achieve reliable zonal isolation and well productivity. With completions covered, we now need to step back and look at the bigger picture, the project and operational challenges that frame all ERD activity. When planning ERD projects, we often find ourselves working with marginal equipment, pushing rigs close to their design limits. Many ERD wells are drilled from older platforms where space and deck load capacity are restricted. This creates real challenges in logistics, pipe handling, and rig up. One issue is racking capacity. With long casing strings, we may need 20 to 30 feet of pipe stretch just to accommodate the length and weight. Mud volumes are also significantly higher, and with larger teams on site, operational efficiency becomes critical. From a business perspective, ERD wells fall into the same cost and risk category as pptx or deep water projects. That means there is heightened corporate visibility and scrutiny. Decisions are tracked closely, and mistakes can have an outsized impact on company reputation and financial performance. At the same time, ERD may be the only economic way to develop small satellite fields or drill in sensitive areas where surface access is limited. That's why ERD sits right at the intersection of technical challenge and corporate strategy. To manage such complexity, we need to take a systems approach. A systems approach is the key to success in extended reach drilling. No single design element or operational practice can be treated in isolation. Instead, every tool and technique must be considered as part of an interconnected whole. Think of hole cleaning as the hub of a wheel. Every other element, from mud properties and pipe rotation to casing and completions, connects back to hole cleaning. If hole cleaning is neglected, the entire system begins to break down. The K&M methodology emphasizes that each component in the toolbox has a knock-on effect. For example, choosing a low-friction BHA design may reduce torque but can compromise steerability. Similarly, a mud program optimized for rheology may affect signal strength of LWD tools. The key is balancing these trade-offs. By looking at ERD through a systems lens, we maximize efficiency, reduce risks, and increase the chances of delivering the well successfully. With that principle established, let's move on to a summary of the technical issues we face most frequently in ERD wells. The first set of technical issues begins with hole cleaning and tripping practices. These are the most critical elements in ERD drilling. Backreaming, while tempting as a corrective measure, often causes more problems than it solves by destabilizing the wellbore and creating vibrations. Instead, we rely on disciplined wiper trips and proper circulation. Wellbore instability is another concern. Here, proactive management and patience are key. Rushing often leads to self-inflicted instabilities. Monitoring shale stability, maintaining inhibition, and reacting early are essential practices. Equivalent circulating density, or ECD, must also be managed closely. In ERD wells, ECD tends to be much higher because of shallow true vertical depth. Formation fracture gradients are lower, leaving us with smaller margins. Trajectory profile design plays a role too. A bottoms-up approach, with cleaning in mind, is more effective than chasing the shortest possible well path. Torque, drag, and buckling are constant challenges, and the calibration of friction factors through real-time data is critical for effective planning. The next set of issues builds on these themes, particularly around BHA and survey design. Continuing with technical challenges, we now focus on the bottom hole assembly and drill string design. Stabilizers need sufficient junk slot area to allow cuttings to bypass, otherwise hole cleaning suffers. We also avoid RPM-limited directional or LWD tools, as ERD wells often require extended rotation at higher speeds. It's rarely optimal to use a single BHA for an entire section. Lighter bottom hole assemblies with jars and hole cleaning friendly designs tend to be more effective. Bit selection should prioritize steerability rather than just maximizing ROP. Mud properties also come back into play, especially maintaining low-end rheology, controlling ECD, fluid loss, and providing inhibition to minimize dispersion. For casing, we must model where casing will stop, anticipate drag and buckling, and use flotation if required. Surveying is another area of concern. Both lateral and vertical accuracy are critical, as TVD uncertainty has a direct impact on reaching the reservoir target. Dual sensor tools, SAG correction, and IFR can all enhance accuracy. With these technical issues in mind, let's consider how patience and risk tolerance shape ERD operations. In ERD, patience truly is the defining characteristic of success. Rate of penetration, circulating time, and tripping speed all need to be approached with caution. Backreaming, for example, should only be used when absolutely necessary, as it introduces instability and vibration. ECD management demands careful circulation practices and controlled pump rates. Any lapse here risks fracturing the formation or destabilizing the wellbore. Similarly, Directional work in both shallow and deep sections takes more time, requiring patience from both drillers and managers. Pipe handling also becomes more complicated. With multiple drill strings in play, every trip takes longer and connections require more care. The diagram on this slide illustrates the balance. On the left axis, we see inclination from vertical to horizontal. Across the bottom is departure length from short to long. Stability and patience are plotted against these parameters. The message is clear. The higher the inclination and the longer the step out, the less margin for error. Having examined both the technical and operational aspects, let's review the module objectives to close this session. Let's revisit the objectives we set out at the beginning of this module. First, we defined what an extended reach well is and how it differs from conventional drilling in both design and operation. We then examined the benefits from maximizing reservoir exposure to minimizing environmental footprint. Next, we reviewed the limiting factors: torque, drag, buckling, ECD management, and well bore stability. For each of these, we looked at real strategies to overcome them, including optimized mud properties, wiper tripping practices, flotation systems, and systems-based planning. We also considered operational areas unique to ERD: casing running, cementing, completions, and project logistics. In each case, the message was clear: ERD pushes equipment and people to their limits, and success depends on discipline and foresight. Finally, we tied everything together with the systems approach, treating hole cleaning as the hub of the wheel and recognizing that no design decision stands alone. With these points reviewed, let's formally close this sub-module. That concludes Module 3 of 3 on extended reach drilling. You should now be ready to complete the quiz for this sub-module. Thank you for your attention and participation, and I encourage you to apply these ERD principles in your upcoming projects and discussions.